Welcome to the first lecture on linear algebra. The first half of our linear algebra textbook focuses on solving systems of linear equations, and the second half will focus on factoring matrices. Okay, so let's start talking about solving systems of linear equations. So here's a sample problem. Find all solutions of real numbers w, x, y, z in r to the fourth. So this is simply 4 real numbers. R here is a set of real numbers to the system of linear equations given by 2w plus 3x plus 4y minus z equals 1, and you have 2 more equations down here. So first thing to notice is that these are linear equations. That means the variables w, x, y, and z, they all occur raised to the first power, or in the case here and here where they're missing, w is missing and x is missing, that's raised to, for example, the 0th power. But there's no x squareds or y cubes or cosine of x or anything like this. So this is what's called a linear system. And we're going to learn in this course a systematic way to solve such equations. And by solve, I mean find or describe the solution set. Now here I've given 3 equations, but there's 4 variables, w, x, y, and z. And so in fact, there'll be more than one solution. And we have to find all the solutions. The key idea is that we can repeatedly apply 3 simple operations to simplify those given equations in a way that does not change the set of solutions, and that will enable us to find the solutions. So here are these 3 elementary row operations. Perhaps they're called elementary because they're fairly simple. You can multiply any equation by a non-zero number. Sometimes I'll call a number a scalar. Another operation, elementary row operation that you can do, I'm labeling it here E2, but that's not standard, is interchange the positions of any 2 equations. And the third operation, it's a little bit more complicated sounding than the other 2, is you can replace an equation by adding to it a scalar multiple of another equation. So let's start with a simpler example than the one I started with to illustrate these 3 elementary row operations, and that we can use them repeatedly in various different orders to find the solutions. So here's a question you probably already know how to do from algebra. Find all solutions in ordered pairs x and y to the system of equations 3x plus 2y equals 7, 2x plus 4y equals 8. Here's how we're going to solve that system of equations using the elementary row operations. Now, this might seem a little bit more complicated than the procedure you already learned in algebra, and that's because this is fairly a simple set of equations. In more complicated equations, like 3 equations in 4 variables, or 4 equations in 3 variables, or even more equations in more variables, the elementary row operations are a great way and a systematic way that you can even program a computer to do. Okay, so here I just listed the elementary row operations again. And again, this numbering is just some numbering I made up. If you ask a mathematician, what's the E2 elementary row operation, they would have no idea which one you're talking about. And all right, so we've got these equations, and we can apply these elementary row operations in various orders, in any order. We can pick any one to do, and they're not going to change the solution set. So what do I mean by that? Well, okay, so here we have these 2 given equations. And then what I decide to do is I notice that this is a multiple of 2, this is a multiple of 2, and this is a multiple of 2. And so then I'm going to take my this E1 row operation and say, well, I'm going to multiply through by 1/2 this first equation. And so when I do that, I get, I've done the arithmetic here, when x plus 2y equals 4. And so I'm going to replace that second equation with 1/2 of it. And so now my 2 equations are this. And it should be pretty clear that we haven't changed the solution set. The x and y that satisfy this pair of equations, the given pair of equations, is the same x and y that satisfy this. We've changed the second equation, but we've not changed the solutions to the pair of equations. And that's the key point. Now, the reason I did that step is to get this 1 here. And you'll see why 1s are quite useful in a second. So the next what I'm going to do is just a simple step of interchanging the two equations. So I'm going to move the second equation up to the top spot and the original equation, the first equation, down to the second spot. Okay, so that's the second operation, the E2 operation. And that clearly doesn't change the solutions x and y. And if at this point you're wondering, well, why did I do those two steps? They seem fairly harmless. You'll see why shortly, but again, there's many other different steps you could have done. So don't worry too much about that right now. Okay, so this one is sometimes called a pivot one. What I'm going to do is I'm going to turn this 3 into a 0 by using E3. That's the more complicated operation where you you replace a row by adding to it a multiple of another row or equation. Sometimes I say row when I mean equation. You'll see why shortly. Okay, so what I'm going to do is take this equation, multiply it by -3 on both sides, and here's what I get. -3x minus 6y is equal to -12. And I'm going to add that to the second equation. And what happens then is this -3x and this 3x here add out or cancel to 0. That's the reason I chose to multiply by -3. This pivot 1 will enable me to cancel or make that 3 a 0 by doing the step here. And so now, using the step E3, I'm replacing this equation by adding to it -3 times the first equation. Here's the computation for adding to the second equation, -3 times the first equation, the -12 and the 7 add up to -5, the -6y and the 2y add up to -4y, so that equation now has come over here. Okay, and then now notice that this equation just has a y in it. It has no x, and that we know how to solve, even by visual inspection. But we can use a elementary row operation. Namely, what we do is multiply both sides of this equation by -1/4. I will sometimes say just divide through by -4. That's what you would do in an algebra class, even when faced with solving this second equation. And when you do that, I've indicated that here, you get that y is equal to 5/4. So we found out what y has to be. And then, just for emphasis, we've got this pivot 1 here. That's how I changed this -4 into a 1. Again, 1s are kind of the goal of the game. We saw earlier that this pivot 1 helped us get rid of this 3x, and then now this 1y is going to help get rid of this 2y here. And so that's exactly what we do next, is we take this row, multiply it by -2, because we're going to try to cancel the 2 here. So when we take this equation, multiply both sides by -2, we get -2y equals -10/4. And then, again, in this E3 step, what I'm doing is replacing this equation by adding to it -2 times this equation. I do the arithmetic here. Here's the first equation. Here's -2 times the second equation. I add. And then, again, the key point was -2y times plus 2y is equal to 0y. The x just stays there. -10/4 plus 4. Well, 4 is 16 over 4. 16 minus 10 is 6. Anyway, the arithmetic, you get 3/2. So this equation here, when you do this elementary row operation of type 3, you get x is equal to 3/2. And now we're done. We found our x and y. Their 3/2 is what x is, and y has to be 5/4. And that's the only solution. Now again, this was probably more complicated than the way you're learned in algebra, but it's a bit more systematic and works in more complicated examples. One way we can make the procedure we just did a little bit faster is to use matrices to avoid having to write down the x's, the y's, the equal signs all the time. So here's the idea. We have these were our two given equations, and we form a matrix where the first row of this matrix, 3, 2, 7, are the coefficients of the first equation. And the second row is the coefficients of the second equation. You have to make sure that the x's are written so the equations are written so that the x's match up and the y's match up. And so then their coefficients would match up. So this first column here is the coefficients of the x's. This is 3 times x, 2 times x, so there's 3 and 2. And the column here is the coefficients of the y. This vertical line, which I'll sometimes forget to write, represents or stands for the equal sign. And then 7 and 8 are the coefficients here. So this is called the augmented matrix. The reason they use the term augmented is that we've included the 7 and 8. Sometimes, for various reasons, we just want to form the matrix of these coefficients. Okay, so then let's see what our elementary row operations that we did translate to. So remember, the first thing we did on the previous slide was take this equation and multiply it through by 1/2. So now it's a row of a matrix, and so this 2, when I multiply through by 1/2, this 2 becomes 1, this 4 becomes a 2, and this 8 becomes 4. And again, I've highlighted the green this 1 in green to indicate that that's what we're after. We're trying to get some 1s, and those 1s, called pivot 1s, will help us turn things into zeros. Okay, so then here we are up here, and then what we did next was just swap these two rows, interchange these two rows. So I brought the 1, 2, 4 to the top row, the 3, 2, 7 down. And then what we did was the elementary row operation type 3. We turned this 3 into a 0 by replacing this row by adding to it -3 times this first row. I've done the arithmetic here. So I've taken the second row, that's 3, 2, 7, and I'm going to add to it -3 times the first row. Here I've computed -3 times 1, -3 times 2 is -6, -3 times 4 is -12, and then I do the addition. The -3 and this 3 add to 0. That's the key point. And then the -6 and 2 add to -4, the -12 and 7 add to 5, and so now I've replaced that row. This 0 minus 4 minus 5 is here. So now this row is all set. I've got this pivot 1 and everything below it is a 0. Then I move on to the next row. I can't do anything to this 2 because if I try to mess with this 2, it'll affect the 1 here and the 0 here. So I've got to work on changing this -4 into a 1. The easiest way is multiplying this row through by -1/4. And so that's what I did here. 0 times -1/4 is 0. -4 times -1/4 is 1. And then -5 times -1/4 is 5/4. Another way of saying it is this: I just divided through this entire row by -4. That's probably an easier way to think about it. And so this 5 became 5/4. So now that I've gotten a 1 here, sometimes I call it a pivot 1, I can use it to turn everything above it and below. There's nothing below, but everything above it into a 0. Because I already have a 0 here, that won't affect the things above this 0. Okay, so what I do is replace the first row by adding to it -2 times the second row. So -2 times the second row is over here. 0 times -2 is 0. 1 times -2 is -2. And 5/4 times -2 is -10/4. I want to add that to the first row. So I do the arithmetic out here in my scratch work. 1, 2, and 4 are copied over the first row. Then I do the addition. 0 and 1 add to 1. -2 and 2 add to 0. These two numbers add up to 3/2. And so now I take this answer and replace our previous first row by that. Okay, and so now the point is we've got what's called reduced row echelon form. We've got a 1 here, 0s below it. Then when we move over to the next row, we've got a 1 in the row after the previous pivot 1 row. And then we've cleared out 0s above that 1. And we can't do anything further. Like, we can't change this into a 0 or a 1 because that will mess up our positions over here that we've worked so hard to get. Anyway, the point is we can now easily read off the solution. This first equation translates to x plus 0y, which I haven't written, is equal to 3/2. And so that just means x is equal to 3/2. That's our answer for x. And then the second equation, remember, means 0x plus 1y equals 5/4. And yeah, why? That means y equals 5/4, because 0x I didn't bother writing out over here. And so we found our answer. So that was quite a lot of work for a fairly simple question. In the next video, I'm going to show how to do the little bit more complicated example I began the lecture with. It was 3 equations and 4 variables. How to do that using these elementary row operations.